Okay, so this project here was one we did with Road Science, who are a division of Downer. They're part of the science part of the transport division, and their expertise is laying our roads. They do about 40% of the bitumen for our coarse chip roads and asphalt. This is a very condensed presentation that I did earlier this year, so I'm going to race through these slides for you. So the problem on this one was hot cutback bitumen emulsion. So when you're putting down a coarse chip sealed road, you spray the bitumen on the road and then you put the stones on top. The hot cutback one is the bitumen thin with kerosene and then heated to 170 degrees. The flash point for kerosene is 40 degrees. They're losing approximately 1 truck a year to fire. Trucks are worth about $1 million. The solution for that is bitumen emulsion. So you take the bitumen, you emulsify it with water, you get a thinner fluid that you can then spray at about 80 degrees Celsius. That's non-flammable. It actually does a lot better job of the sticking of the road into the chips. But there's a lot of inertia in the industry as well. And one of the challenges they've had is to understand what's required to spray at 25 degrees. It'd be really good to be able to spray this stuff cold. Then you don't have to heat up, several cubic meters of bitumen up to whatever temperature for spraying, which is a huge energy requirement. So there's mechanical requirements for the spraying and there's formulation requirements. And the Bitumen person I was working with was a chemical engineer, very much the formulations that he needed to help with mechanical requirements for spraying. So the first thing we needed was a viscosity model for this bitumen. It's highly non-Newtonian, it thins with shear, it's very wide range of viscosity with temperature. We did some tests a number of years ago with Downer on a rheometer. Let's go back. So this machine here is a rheometer. It's a couple of parallel discs. You put your fluid in between, you spin one disc, you measure the torque on the other disc. And with that and CFX, I did a model down the bottom of the rheometer with liquid in, I put water in, a very well known viscosity. I spun it up and measured the torque with the CFD program, put it into the calculations for a standard rheometer, and I came out with an answer that was at least 3 decimal places within what actually went into the calculation. So it did a very good job of calculating out the rheometer itself. The next challenge was to actually take this from a rheometer test of the bitumen. At the top here, we've got the shear rate versus viscosity, and each set of curves is a different temperature. And I managed to fit a Herschel-Bulkley model, which is got a shear stress consistency for cold temperatures. We've got viscosity constant, a time constant, which is your speed, shear rate thing, and then a power law, which sort of changes the shape. And you can fiddle those ones and get a nice match for each temperature, and then did a polynomial fit between the temperatures. So theoretically, at any one temperature, I could actually pick the viscosity of that fluid accurately. That seems to all go together quite nicely. Each one of those has sort of 3 curves, one which is the experimental work, one is a hand calculation from the viscosity, and then the other one is what CFX said it was. And next step was to actually validate this model, because you get a lot of garbage in, garbage out with CFD. And so what we used was a spray truck test rig. So this rig here is a simulated back of a spray truck. The company that makes the spray trucks has got this so they can test their various components. So it's a huge tank of bitumen with a big diesel heater in it. This big U thing here is a Coriolis flow meter. And what we did was we replaced this tube here with the test piece on the right, which consisted of a ball valve and then a perforated disc. The ball valve is very viscosity dependent, so depending on the angle of the ball valve, you get a pressure drop across it. We can measure that, we can model that. Perforated disc is very viscosity dependent. It's got a lot of shear rate in it, shear in the disc, and get a pressure drop across that. And the last bit was for the test, I had to actually model the pipe work back to the tank, because I had to know what the pressure drop was going back to the tank, so I could choose pressure gauge as the test piece. And I didn't want to overdo the pressure gauge, have the wrong readings on it. So we set it all up. That's the test piece in situ. I used a program called Design Expert to do the response surface and the statistical calculations fitting curves to things. And we got an anomaly at about 50 degrees Celsius, and wondering what on earth was going on. And in the end, these are the the constants of the Herschel-Caughley model. And the time constant when my polynomial fit dipped to 0. And of course, when you plot the viscosity, that dip to 0 turns into this enormous spike. It's a little trap for young players. So I fixed that, and all I did to fix that was to adjust the polynomial there, so it sort of fitted the curve better. And then we got a very good match between the valve angle, different pressures, different flow rates, different temperatures. We've got a very good match between the CFX model, that test piece, and the actual experimental work. So the next challenge, this is where it gets fun, was the spray nozzle. This is a standard spray nozzle. It'll spray water and all sorts of things. It's the fluid volume inside it is on the right there. Basically, the spray nozzle is cut across the top with a sling saw meeting a plunge with a ball-nosed drill at the bottom, and produces a fan spray. Did the model, did a mesh optimization to work out what mesh needed. You get away with quite a coarse mesh in the centre where the slug flow goes through the middle, and needed a very fine mesh near the walls to handle the shear inside the nozzle. And plotted out a good characteristic, so we could say, okay, put this polynomial formula into your system calculation, and that will equal whatever a nozzle is doing to that, and flow through it at that temperature. That all worked quite well. That was fairly easily done. The hard thing was actually working out the spraying work. Now, with roadsides, done some experimental work, spraying into a bucket, and they had over different temperatures, pressures, flow rates, and if you plot the Reynolds number at the nozzle, there were 4 regimes that were going on. The first regime down here, which is that top one, is laminar dribble flow, where viscosity is just dominating everything. There's a laminar fan, this zone here, which is the second one down, and that fan is laminar and starts to break up at the end of it. There's a transition zone. This is spray angle Reynolds number, where you get a sort of an unpredictable area of Reynolds number, and it's a sort of not quite one or the other kind of flow. And then the last one is a fully atomized flow. And so sort of understood what was going on there, and then tried to model that with CFX. And it did the laminar at the top, the first zone, the laminar modeled that really well. Then the models start to deviate a bit in shape, but actually when you put in the K epsilon turbulence model into it, you actually got quite a good flow right through the bottom zone, and reasonable correlation going up, but then at the top zone, the transition zone wasn't too good, but actually at the top zone it wasn't too bad. The SSG model did a lot better job of predicting the high Reynolds number lows, but wasn't so good at the low. But we got reasonable correlation, and the understanding that came out of this project for road science, which is really valuable thing, was that you really need to look at the Reynolds number of the nozzle. They didn't really realise that if you calculated that out, that told you what the energy was and what kind of spray you were going to get. And the viscosity model that we created showed that there was an order of magnitude difference in viscosity between 70 degrees and 40 degrees. And if you've got to achieve that Reynolds number there, there's only sort of a couple of things you can do. You can put a lot more flow through there, that nozzle, which is not what they want, because they've got to spread that bitumen at a certain rate of the road through a certain angle. Or you make the nozzle small. If you do that, your Reynolds number goes down, but your speed, or your diameter goes down, your speed goes up. You know, you really get more gain from that. So they're now looking at different spraying technologies, and this works sort of safe and going down the path of ends for trying to work out why it doesn't work at low temperatures. They're really happy with the result.